All right, you guys. Today we're going to begin chapter 11. In this packet are actually chapters 11 and 12. They're both really quick, short sections. Chapter 11, this breakdown, we're actually going to come back to after we learn the whole section. So, like the whole chapter. So we will touch base back on this later. But today what we're going to do is we're going to be talking about section 11.1. And we're going to be working on something that's called the goodness of fit test. It's terrible grammar, I know, but it's really saying like how good or how well does a distribution, a set of percentages, actually fit the whole data set. Okay, so if we estimate percentages, for grades, right, we would estimate 25% for freshmen, 25% sophomores, juniors 25%, seniors 25%, right? Whereas sometimes it's not that they're all at the same percentages. Maybe it's more of one grade and less of another grade or a different category. Okay, what we're going to work on, and we will come back to like these details at different times, right? So like here's one note. Does a frequency distribution or a chart fit a specific pattern? An emergency service may want to see whether it receives more calls at certain times of the day than others so it can provide adequate staffing. That could be a type of example. What we're going to do is we're going to work on something called chi-square. So you've got this cursive looking X. It's chi-square. All right. It's not chi, it's chi. That's the Greek letter chi. And then it's going to be squared, and we'll go through the squared. There is a whole new chart for your chi-squared chart. I'm going to show you how to get that value in your calculator for your p-value. Okay. Our degrees of freedom, I put a note here. We're going to have number of categories minus 1. Our formula, we're going to come back to because it's not really going to make a lot of sense until it's going to look scary, and it's really not that bad. And we're going to come back to this as we cruise through the first example, okay? And then we'll talk about it. So I got you guys, I wrote down for you guys your steps, right? It's still our same 5 steps for any hypothesis test. The first step is to state your hypotheses. What you're going to do is you're going to say like the distribution is, and it's going to be the percentages from the problem, and you're going to state them in the context of the problem. All right. And then your alternate is the distribution is not as stated as above, or you could say at least one proportion is not as stated. Okay, something along those lines, like something's not right. So it's either it is this or it's not this. Okay, you're going to compute your test statistic. I'll go through that. You're going to find your p-value. An important note is that this test is always right-tailed because we're dealing with squared numbers. So squared numbers have to be positive. So our curve for the chi-square distribution is actually 0 on the left and infinity on the right. And your shading is always going to be a right-tailed test, and it's always going to start wherever this line is, okay? And then we're going to go through the same ideas of make your decision and summarize your results. All right, so let's cruise through the first problem, and as we're working on it, I'll kind of fill in those pieces that I told you we would come back to later. All right, so the advisor of the student government at a large college believes that the students at the homecoming bonfire consists of 10% freshmen, 20% sophomores, 40% juniors, and 30% seniors. Okay. Those percentages that are listed are what we're using for our hypotheses. Okay, so our null hypothesis, we're going to say the students at the bonfire are 10% freshmen, 20% sophomores, 40% junior, and 30% senior. You can't really abbreviate it any more than that. All right, that's as short or as brief as we can get. Your alternate, if you remember what we just discussed on the previous page, is you're going to say the distribution is not as stated. Okay. Now, step 2 is we need to find our formula, okay, where we need to figure out our formula. Our formula is, the chi-squared formula, is the sum of our observed values minus our expected values squared over our expected values. Your observed is what you see. So a sample of 100 students at the bonfire consisted of 14 freshmen, 19 sophomores, 51 juniors, 16 seniors. So what I like to do is I like to come over here and I like to create a little table. All right, I observed 14 freshmen, 19 sophomores, 51 juniors, and 16 seniors. Okay. Your expected is the percentage, right? So if we had a sample of 100 students, then, right, that's our total sample size, then we would expect 10% of that 100 to be freshmen. So 0.10 times 100 would give us 10, right? We would expect 20% of them to be sophomores, which would be 20. We would expect 40% of them to be juniors. Keep in mind, it just so happens that I gave you numbers that add up to 100. It does not have to add up to 100. If this was like 175, then it would be 10% of 175. And it's okay if you get a decimal here. Leave it as the decimal. So it'd be 20% of 175, 40% of 175. I just did of 100, so it would be nice mental math for the first time we do this problem. And then we expected 30% to be seniors out of the 100. So we would get 30. So now what happens is once you organize your information, then you can come up with this formula, all right? It's going to be the sum. We're going to add up. There's going to be one of these fractions for freshmen, one of these fractions for sophomores, one of these fractions for juniors, one of these fractions for seniors, okay? So we're going to say, all right, chi-squared equals observed minus expected squared over expected for freshmen, plus observed minus expected squared over expected, plus observed minus expected squared over expected, plus observed minus expected squared over expected. Okay, so you're going to do one for each. So if I gave you 10 categories here, you would have 10 fractions here. Now, when you type these in your calculator, you want to just type it in one shot. All right, so you're going to do a fraction. You're going to do 14 minus 10 squared over 10. Come on, down. Ah, why will my down key not work? Hang on. There we go. Over 10. Go to the right. Plus fraction. We're going to have parenthesis 19 minus 20 close squared. Hit the tab if your down key doesn't work. Plus fraction 51 minus 40 squared. Nope. Hang on. Parentheses squared. Tab over 40 plus fraction 16 minus 30 close squared over 30. Okay, make sure you're adding the fractions together, but you're subtracting up top, and that the subtraction is what's being squared. When you press enter, all right, you get 11.21 as your chi-squared value. It's okay, you're going to get some really big chi-squared values, and that's fine, because if we remember, when we go to work on our p-value, our p-value is always going to be a right-tailed test. So if we have 0 here and infinity here, we have 11.21 and above, okay? To get there, we're going to do chi-squared CDF. So whatever notes you need to take to help yourself out, you're going to go menu. You're going to go stats, number 6, distributions, number 5, and then it's right there, number 8. I can't use my down key for some reason. So you pick number 8, chi-squared CDF. Your lower bound is your 11.21. Your upper bound is your infinity. And then our degrees of freedom we forgot to discuss again, right? So our degrees of freedom on the previous page, we had said that the degrees of freedom are your number of categories minus 1. And you need to make sure you make a note about this. It is not 99. We have 1, 2, 3, 4 categories. So that means that our degrees of freedom are going to be 3. So whatever notes you need to take to remind yourself of what's going on here, we're going to have 3 degrees of freedom, all right, because of our categories -1. And when I press enter, I get a p-value of 0.0106. Okay, from here we have the same situation. Okay, if your p-value is less than alpha, which it is, our alpha was 0.05, our p-value is definitely less than that. That means that we're going to reject the null, which then means what? Okay, the distribution is not as stated. The advisor had claimed this, and we're rejecting this. All right, so you could say the advisor was incorrect. The distribution is not as stated. Right? The advisor stated these percentages and they weren't right. And think about it, right? We were super wrong. Like sophomores was right on the money. Freshmen, not bad, but juniors was really off. We thought it was going to be 40 and it was 51. Seniors were really off. We thought it was going to be 30 and it was only 16. So these two were really far off from what we thought they were going to be. And these two were pretty close to what they thought they were going to be. If they're all really close to each other, your chi-squared is going to be a small number and you probably won't reject the null. But the farther apart these get, then the more likely you are to reject the null because they're going to be so different from each other. Okay, so what I'd like you guys to do now is read number 2. All right, AARP believes that retired senior executives choose as their top leisure activity a particular set of activities. All right, they estimated 38% golf, 32% travel, 23% craft, and 7% read books. To see if these percentages are correct, a local researcher surveyed 300 retired execs and found those pieces of info. So first, you want to state your hypotheses. Okay, so when you state your hypotheses, you're going to pull the percentages out of the problem. Retired senior executives choose these things for their leisure activities. All right, and then your H1 is always going to be the distribution is not as stated above. The next thing you need to do is set up your table, okay, with your categories, your observed, and your expected. I recommend you pause and use pencil and try to set this up right now. See if you can figure it out, okay? As you're setting it up, you should be getting those guys. Golf, we saw 122. We expected, right, so you wrote down all your observed, and you're like, okay, well, if it's a total of 300, we're going to have 38% of 300, 114. 32% of 300, 23% of 300, 7% of 300. Okay, and then we've got to look at this. We've got to set up our fractions. Okay, it's observed minus expected squared over expected. So this is golf, this is travel, this is craft, and this is read. Guys, you got to practice. Put this in your calculator. You should get 3.29. Okay, then go and check out chi-squared CDF. It's a right-tailed test, lower bound, upper bound, 3 degrees of freedom because there's 4 categories minus 1. So we get our p-value here. So if we compare our p-value and our alpha, our p-value is much greater than our alpha, which means do not reject the null, which means AARP was correct and that these are the correct percentages. Okay. So then if we look at this last problem, it's a little different. Okay. Number 3 is saying each observation in a random sample of 100 car accidents at a particular intersection was classified according to the day of the week on which the accident occurred. The results are given in this table. So these are the actual numbers. Actual is another way we can call observed. So you'll notice I added them up to get my total. All right, just like here, I added them up to get my total of 300. I added these up to get my total of 100. Okay. The question is saying, based on these data, is it reasonable to conclude that the population or the proportion of accidents is the same for all days of the week? Now what they've done is they haven't given you percentages. They didn't say this percent and this percent and this percent. They're saying every single day of the week is the same percent. So there's a couple ways we can approach this, right? So the first is, let's write out our hypothesis. Right? The hypothesis is that the days of the week all had the same number or the same percentage of accidents. Okay. The other thing you could do is you could say, wait a minute, there's 100%. I'm going to divide it by the 7 days. I'm going to figure out what that answer is, right? 100% divided by the 7 days would give me 14.29% each day. Okay, if there's 100% of the accidents, right, we're going to divide it evenly over the 7%. That's where that came from. Okay, so now when you go, you don't actually have to set up your table because you already have your observed and your expected are all going to be the same. Your expected, it happens to be that there's 100 of these, so 100 divided by the 7, I used 14.3. So the expected value, if they're all expected to be the same, your expected is the same for every problem. So I used 14.3 for my expected. There are 7 days of the week, so you should have 7 fractions in your equation. Now what you will notice is that I didn't write them all out, right? Here's Sundays, observed minus expected squared over expected. Monday, observed minus expected squared over expected. Tuesday. And then I wrote plus dot 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 plus, and then we've got this guy. If you're able to just put it in your calculator properly without writing all 7 out, I'm okay with that for something this large. Clearly, if there's only 4, you're not abbreviating, right? But 7, sure. But you have to put them all in your calculator. And again, don't do like this, write down the answer, this, write down the answer, because you're going to lose decimals. Just put the whole thing in one shot. All right? When you do that, you're going to get, this is your chi-square. Try it, guys. This is one of those things that you're like, looks easy. And then when you go to do it on your own for the first time on the test, it might not work out so hot. So you have to make sure you can problem solve what questions you have before you move on. We get our chi-squared answer to be 1.08. When you go to do your p-value, you're going to have, it's a right-tailed test, 6 degrees of freedom this time because there's 7 categories. There's my p-value, which is huge, right? So it's definitely not less than alpha, it's greater than alpha. So we get do not reject the null, which means the days of the week all had the same number of accidents. If we're not rejecting the null, then we can say yes, we can conclude the days of the week basically had the same number of accidents. We can't say that they had different. Even though they're different, they're not different enough to be conclusive. All right. Don't do this yet. We're going to work on this in class tomorrow. Okay, or the next class or later. So unless I'm telling you in class to do it, we'll do it that way. See you soon.